Hi, my name is Ayngaran. I'm a PhD candidate at the University of Cambridge, and today I'm going to be talking about some upcoming work with my supervisor, Aaron Wall, as well as my collaborator, Harry Goodhue, who's also attending Cosmology from home, and as well as a follow-up paper by myself, which will come out with this paper, hopefully on arXiv very soon. So thank you very much to the organizers for giving me the opportunity to share this work, which I'm really excited about, and I hope you will be too. So let's begin. So the title of this work is the Cosmological CPT Theorem. So let's start from basics. In cosmology, a fundamental question that we're trying to answer is, where did we come from? And to answer this question, we search for patterns in the sky known as cosmological correlators. And my job as a theorist is to explain and guide the surveys carried out by my fellow observational cosmologists. And so far, we've made significant progress on the theory side using continuous symmetries to constrain correlators. And the paradigm that we work with is known as inflation. So inflation is a theory which tells us that in the early universe, the universe expanded exponentially, and this is described by a quasi-de Sitter expansion. And at the end of this expansion, which generated quantum fluctuations, we then had correlation functions which imprinted themselves on the cosmic microwave background, and then later those then grew into the large-scale structure, which we then observe in our sky today. And we have predicted and measured the scalar 2-point function, which was measured in terms of the temperature correlation function of the cosmic microwave background, as well as the matter power spectrum in the large scale structure. And we hope to now go on and predict and measure the graviton 2-point function, as well as higher point correlation functions of the scalar and graviton functions. And we hope to measure these soon in the upcoming surveys. But a fundamental question that we might want to ask is, why does our universe expand, and why does it expand in the early universe? And why is there only matter? In flat space, there's a fundamental discrete symmetry known as CPT, which the expansion of our universe and the lack of matter naively seems to break. But in this talk, I will explain how CPT actually does arise in cosmology. So the plan of this talk will be to look at the original CPT theorem in flat space and understand what is required for CPT invariance. And then I'll use something known as embedding space formalism to identify an analogous CPT theorem in cosmology. And from then on, I will go on to think about the CPT theorem in a novel way where we can then make converse statements. And then I will describe the constraints that we can get from CPT on cosmological observables. And then I will show that CPT invariance actually strongly constrains parity violation in cosmology, which has been of recent interest in the observational side. And then I will discuss the implications of the cosmological CPT theorem for the early universe and quantum gravity. So the conventions I'm going to be working with to be consistent with and hopefully avoid confusion is that I'm going to talk about both CRT, which involves flipping one spatial direction, and CPT, which involves flipping all spatial directions. Now, CRT and CPT are actually equivalent if you have rotational invariance, because rotations flip, a 180 rotation is equivalent to flipping two spatial coordinates. So in even space-time dimensions, CPT and CRT can apply one another. Now, I'm going to be working with the convention that space-time dimensions are denoted by big D and spatial dimensions by little d. Now, I will use the terminology Lorentz invariance, and Lorentz invariance just simply means is the theory that's invariant under SO plus 1 comma D, which is also known as a proper of a Cronus-Lorentz group, i.e. the transformations which preserve the orientation of time and space. And similarly, a de Sitter invariant theory is one which is invariant under SO plus 1 comma D plus 1. And I'll be working in a real basis of fields. So complex fields will be broken up into their real and imaginary parts. So the original CPT theorem in flat space tells us that Lorentz invariance and unitarity imply CRT invariance. And there's no converse statements that one can necessarily make. So CRT and unitarity doesn't necessarily imply Lorentz invariance. And this comes from one of the things that this comes from is the fact that the Lorentz boost, when Wick rotated, becomes a rotation group. And this is the important aspect of Lorentz invariance, which then becomes important in the CPT theorem. And in order to Wick rotate to Euclidean theory, we need three specific criteria: that the theory is Lorentz invariant, the vacuum is Lorentz invariant, and the energy is bounded below. Now, as I said, the Lorentz invariance rotates to the rotation group, and this then implies a smaller subgroup, which is the two-dimensional rotation group, which then implies a 180-degree rotation, specifically the choice of the rotation parameter being pi. And it's this 180-degree rotation and unitarity, which then implies CRT in Lorentzian signature. And then with rotations, we can then get CPT in even dimensions. And this then tells us we only need the SO2 subgroup, which comes from, in Lorentzian signature, the SO plus 1, 1 subgroup of SO plus 1, D. But we also know that de Sitter invariant theory also has this subgroup of SO plus 1, 1, because this is a subgroup of SO plus 1, D plus 1. Therefore, there must be an analogous CPT theorem in de Sitter. But then the question is, what is the SO plus 1, 1 boost in cosmology and the 180-degree rotation? So to answer this question, we're using embedding space formalism, and through the embedding space formalism, where we embed de Sitter in a one-dimensional higher flat embedding space, we find that actually using these relations, the SO plus 1, 1 boost is actually the dilatation generator, or as cosmologists call it, it's just the term for scale invariance, generator for scale invariance. Therefore, in cosmology, we analytically continue dilatations to get the 180-degree rotation. And this then takes us from one Poincare patch and relates it to another. So essentially, it relates an expanding patch to a contracting patch from the perspective of the global time-like Killing vector, from the perspective of the global time vector. And dilatations play the role of Lorentz boost in the CPT theorem for cosmology. And this is very important because this means that we don't actually need the full de Sitter boost in cosmology in order to obtain CPT. And this is very relevant for phenomenologically relevant models of inflation because these generally break de Sitter boosts. Therefore, in flat space, we have the CPT theorem that Lorentz invariance plus unitarity implies CRT, but in cosmology, we have specifically dilatations or scale invariance, and unitarity implies CPT. And the reason why I say CPT in cosmology is because dilatations always flip all the coordinates, and therefore CPT does, therefore, regardless of dimensions, you always get CPT. And now I'm going to be identifying what we mean by unitarity in cosmology by changing gears and now rethinking the CPT theorem for flat space to make converse statements. And to do that, we're going to first start off by identifying that in Euclidean signature, unitarity implies reflection positivity, which is simply a statement about the operators on one side of the Euclidean tau equals 0 plane and their reflected operators giving a correlation function which has a positive norm. But we can weaken reflection positivity to give reflection reality. So this is a theory with both positive and negative norms in Lorentzian signature. And we then see that all endpoint correlation functions in a reflection real theory are actually invariant under a discrete symmetry, which I'm going to call reflection reality. And we can use reflection reality now to think of the CPT theorem in terms of a Z2 times Z2 group structure. So rethinking the CPT theorem for flat space, we can now take these three discrete symmetries that we've identified from unitarity, which gives us reflection reality, the Lorentz invariance, which gives us the 180-degree rotation, and finally the final discrete symmetry of CRT. And we see that any two of these discrete symmetries imply the third, and all three combined together to give the identity. And therefore, in flat space, we not only have the original CPT theorem, but we also now have converse statements. And the constraints of these discrete symmetries on the observables in flat space, such as correlation functions, are depicted in this table. So what reflection reality is, which is implied by unitarity, does is that it relates a correlation function, a time-ordered correlation function, to an anti-time ordered correlation function with a complex conjugation. And similarly, CRT also relates a correlation function to an anti-time ordered correlation function to an anti-time ordered correlation function with an overall complex conjugation, but also flips one of the spatial coordinates and the time coordinate. And then the 180 rotation, which is implied by Lorentz invariance, preserves the time ordering, but flips one of the spatial coordinates and one of the time coordinates. And now we can similarly construct a table for cosmological correlators and cosmological observables, such as the wave function. But instead of the 180-degree rotation being provided by Lorentz invariance, we're going to find that as provided by dilatation variance, as we saw previously. And as I mentioned before, because dilatations expand all the coordinates, we end up flipping all the coordinates. And so there's not just one spatial coordinate flip, and you always have CPT in cosmology. So the observable that I'm going to focus on is specifically the cosmological wave function. So the cosmological wave function is a probability distribution for the state of the universe as we observe it in the sky. So to compute this probability distribution, we work with a Q of t and curve space-time path integral, which just integrates over the various paths the field from inflation could have taken, and with the specific boundary conditions in the infinite past, which for purposes of this work, we work with a Bunch-Davies vacuum, and a future boundary condition that the field just takes on a specific profile at the end of inflation. And this field can be any specific spinning field. So this could be a scalar field, which then gives rise to temperature fluctuations, or it could also be the graviton, which then would lead to the graviton fluctuations, which we hope to measure. And to compute the coefficients of this wave function, which we call the wave function coefficients, we use perturbation theory, where we expand the action in terms of the free and interacting part, where the free part leads to the leading contribution in the Gaussian signal that we see in the 2-point function, and then the interacting part then leads to the leading contribution in the higher point correlation functions. And these wave function coefficients depend on the Fourier space momentum, as well as the magnitude of the Fourier space momentum, which we sometimes refer to as energies in the literature. And we can then use these wave function coefficients to compute cosmological correlators. Now I'm going to explain how we can constrain these wave function coefficients from using CPT. And from these constraints, I'm going to be able to make robust predictions for the actual observables of cosmological correlators. So in order to come up with important constraints, we not only have to use what I've described as the discrete symmetries, the global discrete symmetries of CRT, but we also have to have discrete symmetries locally. And you should refer to the paper to learn more about why this is important. And these then lead to very important fundamental discrete symmetries which hold non-perturbatively and constrain the wave function in this particular way. Where particular of importance is that the magnitude actually gets flipped in the discrete symmetries of reflection reality and the 180 rotation, which kind of is analogous to how CPT relates a particle positive energy to a particle negative energy in flat space. And CPT is is a particularly interesting discrete symmetry, which also holds at the level of the full wave function. We can write it in this particular form where the wave function is related to its complex conjugate with the time flipped. So a wave function at the future boundary at the end of inflation is related to the past boundary of a contracting universe. So we've derived a CPT theorem in cosmology, specifically that scalar invariance and unitarity imply CPT, as well as converse statements. And it's these converse statements which can then lead to powerful constraints on the wave function coefficients. And one particularly interesting thing one can do is completely determine the phase of the wave function coefficients. And it has this particular closed form, which holds for any spatial dimensions as well as non-integer dimensions and any loop order and any mass field for any endpoint correlator. And for the particular case of massless scalar fields, as well as gravitons, we find that in our universe for d equals 3 spatial dimensions, there is no boundary parity odd correlators. So the only way to get parity odd correlators is from either IR or UV divergences, where IR divergences just mean that we don't go all the way to the boundary and finish inflation at some finite time. And UV divergences come from essentially lead to an expansion in fractional dimensions or a renormalization of the mass of the fields. So to conclude, we've showed that an analogous CPT theorem exists here in cosmology, and we've derived a novel way to think about the CPT theorem to make converse statements. We showed non-perturbative constraints of the CPT on the cosmological observables, and we use these constraints to completely determine the phase of the wave function coefficients for any theory, and in turn derive a no-go theorem for parity violation. And some important questions that this leaves us with is that we know that our universe slightly broke scalar invariance, and we believe that the evolution of the universe was unitary, but the converse statements from the cosmological CPT theorem tells us that this means that our universe must have slightly broken CPT. So what does it mean for the universe to slightly break CPT? And this then tells us that the slight breaking of scalar invariance, which is related to slight breaking of time reversal symmetry, is also related to the matter-antimatter asymmetry, or specifically CP violation. So these are all intrinsically linked. So maybe the arrow of time is then therefore related to this. This shows a fundamental relation between the arrow of time and baryogenesis. And another question this leaves us with is CPT asymmetry of quantum gravity. And some of my upcoming work on this front in holography seems to suggest that this is true. Thank you for listening, and see you at the discussion session on Thursday.